Mr. Gene Oliver, Deputy Project Manager, Marshall Space Flight Center, Dr. Ed Weiler, Program Scientist, NASA Headquarters, and Dr. Peter Stockman, Deputy Director of the Space Telescope Science Institute. We'll start with Mr. Broom.
As those of you who are participants in our what we call the 400 Club, remember we were last few weeks aligning the telescope. We had gotten to the point where we had pretty well put the problems that we've been reading about and writing about earlier behind us. We had our pointing problems were pretty much in hand. Motion in the roll axis and the XY plane had gone away as we had focused. And we were dealing successfully with the transitions from day to night and night to day. We were very few times where we were losing acquisition of signal during those transitions, so we had that pretty well under control. We had finished the course alignment and the first light activity, I guess a little over a month ago, and we were in fine alignment with the telescope. 2 weeks ago, we had come to some conclusions on a set of movements to make with the secondary mirror that we thought would put us into a good focus. And these were motions along the XY, along the barrel of the telescope axis in the XY plane and in tilt. So a very aggressive set of movements were made on Thursday night about 2 weeks ago. Should have significantly improved the image, but it did not. So that set us back to trying to understand what was it that had happened or not happened. Okay. Okay, is that any better? Not much. Okay. All right, we went back and reviewed the data from that we'd use as a basis of the what I defined as an aggressive set of measurements, and decided to go back and do a very systematic set of movements of the secondary mirror, moving well back from focus, intermediate steps through focus, and then intermediate steps on the other side of focus, each time taking pictures with the planetary camera after each motion, and we took some FOC, some plain object camera pictures as well. The conclusion we've come to from that is that there's a significant spherical aberration appears to be present in the optics, in the optical telescope system optics. Now, some people asked me earlier today, what is spherical aberration? The simplest way of understanding it is that when you have a mirror that's focusing, the light all comes together at a single point is the objective of the exercise. You want the light to come together and focus at a single point. When you have spherical aberration, it says that there's some disfigurement of that mirror that causes the light, instead of focusing at a single point, to be spread across a region in space. And that is spherical aberration. So Gene is going to talk to you a little bit more about this, and I'll pass it over to Gene right now.
Thank you, Doug. The specific activities that we're involved in at the time we began to strongly suspect spherical aberration was a process of focusing the telescope, as Doug mentioned. You would think that it would be pretty straightforward to find a focal point for a telescope, and indeed as we set out to do this, it seemed like a straightforward activity. However, as we began to get further into this, we began to realize there was no one specific focal point that was optimum. There were a series of focal points, each of which was giving us an image which was not meeting the specifications we needed, yet each of these points had a little different characteristic. We then backed up and decided that what we needed to do was to go all the way through focus from one end to the other, extremely out of focus in both directions, and therefore learn some basic facts about the performance of the optical system. The first fact we learned was that the system, as we went far out of focus, gave us a very good view of the pupil function of the telescope. In essence, we've gotten a picture, if you will, of the primary mirror with the telescope well out of focus as reflected by starlight. So we could tell from that the aperture was clear and that the system was not grossly deformed in any way. Now, this seemed like an obvious question to us. We didn't know at the time what the problem was, so we felt, let's go back to the very fundamentals of it. At the same time, as we went through focus from one end to the other, we got a very clear and distinct characteristic, a textbook characteristic, if you will, of an optical system which had a significant amount of spherical aberration. We then began to take a series of specific photographs with the PIC, and on one occasion for their first light picture with the FOC, and with a team of scientists from the Institute and from the Wide Field Planetary team, as well as Hughes, the prime contractor for the telescope, and a number of NASA folks, we worked for several days deconvolving these images to determine if we could pinpoint exactly what the problem was. All of this effort, after several days of work, began to conclusively point to the spherical aberration theory that we began to see as we went through focus on the telescope. A day or so ago, it became obvious that this was a problem. And for a while, we began to be concerned if we were picking up problems in the WFPIC and not in the OTA, but that was not the case. It took us literally up until about yesterday or so to really conclusively determine this. With that behind us, we are now in the process of evaluating the ramifications of this. We've determined from analytical work that I just mentioned that we have approximately a half a wave of spherical aberration. This amount of spherical aberration will keep us from meeting one of our many level 1 requirements. And it's an important requirement, and it had to do with the ability to focus a large amount of energy in a small point. We're now in the process of finalizing the alignment, however, because at this point in time we've dropped all of the alignment work except the fundamental investigation of this particular phenomena that we've identified. At this point in time now, we're going to go back to the normal routine that we had in place to finish the alignment of the system. That entails gathering more data from the cameras. Next week, we will be gathering more information from the FOC. We will use this data along with the figure sensors to complete the alignment for coma and astigmatism. So within a week or so, we should have that portion of the alignment completed. When we are completed with that, we shall then find that we probably will have, if our theories are correct now, a residual amount of a spherical aberration to deal with. The decision still ahead of us is how do we deal with that? We have a couple of alternatives. One alternative is to utilize the primary mirror actuators that are on the primary mirror. The only way to remove this particular aberration is to change the figure of one of the two mirrors. We don't have the opportunity, but by design, to change the figure of the secondary, so we must attack the primary mirror with the actuators that are now provided there. One of the drawbacks to this and the limitation of this is that these actuators were designed to take out astigmatism and other types of aberrations which would involve moving the mirror in its weaker planes. To change the mirror to take out spherical aberration is trying to flatten the mirror out and move it in one of its stiffest directions to be moved in. So there's going to be a limit to how far we can go with these primary mirror actuators. We can probably take out only a small fraction of it. The primary thing left then is to consider two things. What can we characterize the performance of the system and begin to evaluate how it fits in with the science program we have planned, and Ed will talk to you more about that. To also look at the optimization of the focal point, because as I explained, different focal point positions gave us different image qualities, and we can look for optimum image positions so that we can optimize the amount of science or maybe even tailor it for the kind of science we do. The next alternative, and one of the things that we're probably going to institute, will be to feed this information into the advanced SI development program so that the advanced scientific instruments that have come along after this will essentially be able to eliminate this problem, and any residual spherical that we have in the mirror will be then taken out by optics that can be provided in the front end of these scientific instruments. So the course of action we're on today is essentially unaltered from our original course of action, that is to complete the alignment of the mirrors. And we're here today to tell you that we will probably have some residual aberrations, and we're going to have to deal with these, and we still have a number of ways that we can. Some of these ways involve the modification of advanced instrumentation to come next. So our challenge now is to begin to get enough data together so that we can make these final decisions in the alignment process, and then ultimately provide very essential data on the performance of the system to the scientific community and to the scientific instrumentation so that they can involve this then in their follow-on design work. I believe probably this leads maybe directly into the discussion of the scientific side of things, and Ed Weiler will give you that information.
Thanks, Gene. I'm going to try to give you a perspective on the short-term ramifications of this particular issue and also the long-term ramifications in terms of what we can do, the science we can do, the science we won't be able to do for a while in the short term, and most importantly, the solutions to this problem in the future. I spent the morning with the Science Working Group, which is a group of about 20 So what I'm going to report to you today is the result of that discussion with the scientist. And it's very preliminary, but I think it's as accurate as you can get in 24 hours. To put things in perspective, let me remind you that Space Telescope, because of its capabilities, was already 10 times oversubscribed. That is, we had 10 times the observing proposals that we could have ever accomplished in the first year alone. And we expected that once we started observing, that oversubscription ratio would have increased. I guess the important question in light of all this is, can we do unique and important science? That's the most important question. And the answer is an emphatic yes. We can still do important and unique science. 100% of the time available to Space Telescope will be used doing important and unique science until we can solve some of these problems. To put things in perspective, we had 3 important specifications on Space Telescope in terms of why it was unique among other ground-based telescopes. Spatial resolution, the ability to take very fine images, and that's what we're talking about today that's impacted, and I'll get back to that in a minute. One thing that's not impacted is its ultraviolet capability and its infrared capability. It has that just because it's above the atmosphere. The other thing is because it's above the atmosphere also is that stars don't twinkle, and it has very steady images, and whether the stars are very small or very large, they still don't twinkle. In terms of the spatial resolution, the ramifications of what you've been hearing today is that the original spec was that we would have about 70% of the starlight's energy in a circle around 0.2 of an arcsecond. Right now, in that little circle, we're getting maybe 10, 20, 25% at best, depending on where we put the focus. The 70% criteria isn't met until we get out to about 1 second of arc or so. So that's how much we're out. And that's about ground-based resolution. So currently, we're running about ground-based resolution in terms of encircled energy. But again, keep in mind the UV infrared capability and the steady images, because that's what I'm going to be referring to in the next few minutes. Okay, what I propose to do now is go through each instrument and tell you what we can do, what we can't do, and I'll conclude with what we're going to do about it. The Goddard High Resolution Spectrograph is an instrument that only works in the UV. It does science that cannot be accomplished at all on the ground. With a little more observing time, because the images are bigger now, we will probably be able to do most of the science that the HRS, the High Resolution Spectrograph, originally proposed. The only science we will not be able to do is science in very crowded fields where you wanted to take spectra, break up the light of stars that are very close to each other. We won't be able to resolve those, but that was a rather small fraction of the science of the HRS. And perhaps interesting is that planetary features, it'll still be an excellent instrument for planetary features. Things like the red spot on Jupiter, the polar caps on Jupiter, are fairly large features. They're actually larger than the resolution we're talking here. So that kind of science will not be impacted either. So the HRS is probably our least impacted instrument as far as we can tell at this point. The faint object spectrograph also is a UV and visible instrument. In that case, again, the ultraviolet science will not be impacted except when it was trying to do science on very tight, crowded fields. But a very important piece of its science, namely looking at quasar absorption lines, that is, if you use a quasar as a background source and want to look at the intergalactic gas, the gas that new galaxies might be forming out of, that science will not be impacted at all because those are point sources. And we want to look at that in the UV, which again cannot be done on the ground. So in that case, we'll be okay. Faint object camera, the European camera. It was our most, it had the highest spatial resolution of all our cameras. In the visible now, again, the resolution won't be that good. It'll be about ground-based. Except for very bright, high contrast sources with some fancy image processing that can be done on the ground, we might be able to get back some of that resolution and beat ground-based by some significant amount. We think we can do that, but we're not sure yet. We have to do some more analysis. In the ultraviolet, it's still totally unique. We have no consistent capability in space to take ultraviolet images. The only capability that's similar is the ASTRO instrument, the Ultraviolet Imaging Telescope. It'll fly for 10 days, hopefully in August, but its resolution is about 4 or 5 times worse than what the faint object camera can do, even in this degraded condition. Okay, let me turn to the HSP, the high speed photometer. Here we were taking advantage of all 3 of those things. That is, on the ground it's hard to do very accurate photometry because the image scintillates, it twinkles. We won't lose that with the problem we have now. We'll still be able to do visible and UV variability measurements, very high time resolution. The only things we will not be able to do are things where we need science programs where we need very, very high signal-to-noise or very careful measurements, because the image is larger and we won't get as much light per unit time. So we'll lose some of that science. But in general, we'll still be able to do perhaps half of the science that the high-speed photometer originally proposed, and primarily in the ultraviolet. The one instrument where we have a major problem, of course, is the Wide Field Planetary Camera. It's not a very good UV instrument. Its prime science is going to be done in the visible portion of the spectrum. We feel right now that there's probably no real science that we can do with the Wide Field camera at this time. It's primarily a visible instrument, not a UV instrument. The so-called sixth scientific instrument is a collection of 3 fine guidance sensors to do astrometry, the ability to measure objects very accurately. The good news there is that we feel right now that we will probably be able to do 100% of the science we originally proposed. It doesn't depend on the high spatial resolution. This is important because one of the key things we sold the program on was looking for planets, and we always said even though we might be able to image a planet with one of the cameras, the real way to find planets was to look at stars as they move in space and look for the wobble. You do that with the astrometry instruments, and we feel the astrometry instruments are still okay and we'll be able to do 100% of that science. Okay, the bottom line is, do we have a fix for this? As I said, the biggest impact right now is the loss of spatial resolution, the wide field camera. We feel that we can characterize the problem, the spherical aberration problem, well enough that we can take advantage of an insurance policy that we haven't talked much about, and it hasn't been in the press much, and that is we started a long time ago to plan a maintenance program. That is, every 3 years we plan to go up with the space shuttle, change out instruments, change out things that broke, the gyros or something might break. We have gyros in stock. In fact, we have in stock, in storage, most of the critical components on Space Telescope. Right as we talk now, we are building a second wide field camera. And it's not too late to put a corrective optic. You can almost think of it if you've got bad myopia, which you can say our telescope has now, and you put your glasses on, you can correct totally and get 20/20 vision. That's what we would do in the wide field camera, the second wide field camera. We would change one little mirror, relay mirror in there, take out the aberration that the primary mirror causes. That is, if it's a positive aberration, we put in a negative aberration and basically cancel it out. We feel the analysis is only preliminary, but we're pretty optimistic that we can take out all the aberration with the second wide field camera and get us back to the original specification. I might remind you that about 40% of all the science that we've ever talked about on the Space Telescope would be done with a wide field camera. Right now, the plan for that second wide field camera is to be ready about 3 years after launch. You might guess we've already asked the JPL project to start looking into how early they could have that before 3 years. But I think within 2 or 3 years we could have a replacement wide field camera ready that would bring back a good deal of the original science of the Space Telescope. The second instrument that we are already in the process of developing is the so-called NICMOS, the near-infrared camera and multi-object spectrometer. Right now we have no infrared capability, and we hadn't planned to have infrared capability until about 6 years after launch. We are already asking them to look at, and they've already given us a preliminary analysis that they could also correct for this problem and get all the capability that they originally thought they could get by, again, corrective optics. So in about 5 or 6 years, we would get our original infrared capability, which again is not, you can't do that from the ground. We should be able to get that in the longer term. In terms of the faint object spectrograph and the high resolution spectrograph, where we're losing only the science that you lose because you don't have the high spatial resolution to separate very close objects, we have something under development called the STIS, the Space Telescope Infrared Spectrograph. The good news there is that, again, preliminary analysis shows that with some corrective optics, we can take out this aberration and meet the full specifications of the STIS. It replaces both all the capabilities of the FOS, the HRS, and as an added benefit, it has the capability of taking images, and images to the quality of the faint object camera. So in 6 years, we might even be able to get back those visible capabilities that we do not have anymore in the faint object camera. Let me conclude by saying HST was and is a difficult challenge for a tremendous payoff. Although we're all, it would be dishonest of me to say this, the mood of the scientist is very happy right now. We're all frustrated, obviously. But after our meeting this morning and hearing where we are and hearing that most of this aberration, if not all, can be explained by spherical aberration, and that we should be able to fix it in our insurance program, I think we're all committed. Nobody's walking away. I think we're all committed to work on it and do it right. And I'll stop there.
Okay. Before we take questions, we'll hear from Dr. Fisk, that's Associate Administrator for Office of Space Science and Application.
Thank you for the promotion. Just a couple comments. One of the things we need to do, of course, is to figure out how this problem occurred in the first place. And NASA, of course, has a fairly formal process for doing that. And so we are constituting a review board, which we are calling the HST Optical System Review Board, to essentially determine what happened that caused for the mirror or whatever reason to have this, what's my term here? Aberration, thank you. The board is going to be chaired by Dr. Lou Allen, who is the director of the Jet Propulsion Laboratory, and we will be announcing shortly the members of the board. And we will ask them to go back essentially into history. In some cases, these events could have, that caused this issue could have occurred as much as 10 years ago, back when the mirrors were developed in the late 70s and early 1980s, and to determine how this in fact happened, and of course to derive lessons from it, some of which could impact the designs of these replacement instruments. But I think the point I want to make most important here is that NASA prides itself in responding to challenges and overcoming the challenges. Now, I'm not sure all the things we're going to do to make the Hubble Space Telescope work exactly like we want it to, whether it's adjustments in the primary mirror, whether it's data analysis and deconvolving of the data, whether it's replacement instruments, whether it's replacement instruments on a faster time scale. But I know we're going to succeed at this, and we're going to turn the Hubble Space Telescope in all regards into the exciting scientific instrument that we expect it to be.
Thank you. Now we'll open the floor for questions. Please state your name and affiliation before asking the question. John?
John Holloman, Cable News Network. I don't know exactly who to ask. What might have made this happen? What are the possible things that could have happened to make this mirror not look like, a spherical mirror anymore?
Gene, can you take that?
Well, the design of the optical system we know is sound because the optical prescription, if you will, has been provided to all of the scientific instrument developers, and they've developed equipment to feed their instruments with the same image that the OTA provides, and it's all worked well. So we know that the design is correct. Where we suspect, and I have to emphasize the word suspect because we don't know, is that in the metrology used, that is the techniques that are used to measure the figure of the mirror and polish it and hold it steady while you're doing that, somewhere in this chain, a very complicated chain of events, there was a mistake or an error made somewhere, either in the primary mirror or the secondary. And it resulted then in the mirror being very precisely made, but ultimately to the wrong figure. And that's the best we can tell right now. And it's just the process of finding this out is just beginning, really.
There's no way the mirror itself could have changed during launch or after the telescope was up there. It had to, as far as you know, it had to have happened on the ground before it went up?
That's correct, because the aberration is so textbook perfect in some symmetry that it couldn't be just a sag or some random kind of a problem with friction in the mount or something like that. It's something that it looks, if you look at the images and you look at the way we can mathematically reproduce them, they're so textbook clear that it was done, I hate to say this, but on purpose. I mean, it was done very carefully, but it was done to the wrong figure. and we don't know whether it's primary or the secondary yet.
You know, one point that you might make, Gene, is that although we describe this as having, you know, a separation at the points at which the various parts of the mirror focus, you know, it's important to understand what type of distance that is. I mean, it's, as I understand it, we're half a wave out, which is, if you try and translate that into human terms, you're talking about 1/50th of the width of a human hair. I mean, that's the kind of distance that the spread of the light is at the focal point.
Okay. The young lady first, and then we'll come to you, okay?
I'm Mary Wolf with NBC. Is it possible that you could bring the telescope back as opposed to fix it in space?
It's possible, but I really, it doesn't appear to be a practical thing to do because of the danger of contamination of the optics and the resultant loss in ultraviolet performance, just the cost and the risk in handling the hardware. That is certainly an option, but we feel that it's, at this point in time, we don't feel it to be a practical option.
I think as long as you can, if I can follow up on that, as long as we can do unique and important science in the next 2 years, you have to balance that off versus bringing it down and letting it sit on the ground for 2 or 3 years.
It's still a unique machine. I mean, there's no question about it.
There are some people who say that the testing that was done on the ground, if their testing had been, not all the testing had been done on the ground, that possibly some of the problems wouldn't have occurred. Do you have a reaction to that?
I'm sorry, I couldn't understand
That
your
the
question.
testing for the telescope was done on the ground.
Yes.
Is there any reason as to that possibly some of the testing could have been done, that this wouldn't have happened had the testing not been done on the ground?
All the testing that we had planned in our baseline program to carry out was completed and done in some cases more than once. The care that we used in reviewing and auditing, if you will, all of the analytical work that was done in designing the mirror system, the reviews of all the hardware that was used to support the mirror, and the mathematics and the software that was used to reduce the data during the processing of the mirror was all gone over very carefully by many people, because we knew that this is something that had to be done very carefully. But in spite of that, we still have this problem.
Earl?
I just want to clarify, do you know for sure that the aberration is in the primary mirror, the secondary mirror, both?
No, we don't. All we know is that it's in one of the two mirrors, probably not both, but certainly in one, but we can't define which it is.
And it's an aberration that's across the entire size of the mirror. I mean, it's the whole shape of it is slightly wrong rather than bumps or something or problems in
Right.
regions of the
It's a
mirror.
radially symmetrical departure from the true figure that you want.
Okay, I'm here.
Yes, I'm Ed Chen from the Los Angeles Times. I think my question goes back to the one that this lady asked, which is, if this aberration was such a perfect textbook case, why wasn't it caught on the ground if you think it did occur on the ground?
It's because on the ground, in the testing we did on the ground, we did not measure or test the two mirrors in combination. To test the total telescope with the primary and secondary so that you get a total test of the end-to-end optical system is an extremely costly and a very complicated thing to do, because really the only practical way to do it is to build a large flat and put it in front of the mirror and look through the optics to this flat and then back again through the optical system. A flat of that size is tremendous in size, and just the process of building a flat that had the precision you need to carry out such a test is a horrendous activity.
Give us an idea.
Hundreds of millions of dollars. It's an extremely costly process.
Please wait for the mic for you. You can ask that a little later. Mitch?
Mitch Waldrop, Science. I guess I'm confused. You're telling us that the resolution is not as good as on the ground, yet I see these pictures which we've been mailed out here showing which seems to be a phenomenally better resolution than on the ground.
Well, let me explain something. The image quality, there have been many ways to define the image quality, but we find that we have an image which has a characteristic shape, that you have a bundle of energy. The largest quantity of energy is